Okay, so today we'll talk about Ampere's law and its applications to calculating magnetic fields. In this slide, you have four integrals describing our electromagnetic fields. Okay, so you have this equation right here, which is our well-known Gauss's law. Okay, so this means that you have an electric field passing through some arbitrary closed surface, okay, sourced by this charge enclosed. Okay, so what we have been doing, however, is to consider highly symmetric charge distribution such that this surface integral here turns into a simple product. Okay? So having a simple product on the left-hand side, we can easily calculate the electric field. Okay. So we also have one integral describing electric fields, which is now this integral right here. So this is a closed loop integral, which means that for any closed loop that we consider, any size and any shape, the total line integral of the electric field about this closed loop is always zero. So we attribute this behavior or this result to conservation of energy, okay? Which is only applicable, however, for electrostatic fields. We will talk about non-electrostatic fields at a later time. Okay, so now let's move to this equation here. Okay, so this one. So here we have a zero magnetic flux through an arbitrary closed surface. Okay, so this is not very helpful in calculating the magnetic field, since even if we have arbitrary distributions that source magnetic fields, this term here is always zero. Okay, so now we turn to another integral which has this form here. Okay, so now we have a magnetic field projected through a closed loop. We want to find the total sum or the total line integral around the closed loop defined by this dl here. The question now is, what is this right hand side? Okay, the answer now is given by the equation displayed, where you have the line integral given by this equation, okay, proportional to the current enclosed by that arbitrary closed path. So it's this one. Okay. So we have this proportionality constant. It turns out to be the permeability of free space that we also saw in Biot-Savart law. Okay. So we make a comparison with Gauss's law and Ampere's law. So in Gauss's law, both sides gives us the electric flux. So the closed integral on the left-hand side is a flux. This simple expression on the right-hand side is also a flux. Okay. However, Ampere's law does not contain any information about the magnetic flux. Okay. The magnetic flux is given by this equation here, which is always zero. So we do not have a special term for the left-hand side of Ampere's law. We'll just call this one the line integral or the closed path integral, which is proportional to the enclosed current given by this quantity here, I enclosed. Okay, so we make the following comparisons. You may stare at them. Comparisons between Gauss's and Ampere's law. So in calculating electric fields using Gauss's law, we choose a special Gaussian surface, which is a highly symmetric surface that turns this equation here, or this expression here, into a simple product. So in Ampere's law, we'll also consider a special loop or special integration path called the Amperian loop. So in this Amperian loop, this line integral here, okay, where we project the magnetic field onto the closed path that we consider, we turn this expression into a simple product. Okay, so let's look at an example on how Ampere's law is used. Okay, so look at this figure right here. You have three current sources, I1, I2, and I3. I1 and I3 point up, I2 points down. Okay, so we now enclose these three currents in an integration path where we apply Ampere's law. So as a rule of thumb, no pun intended, we curl our four fingers to the direction where the Amperian loop is traced. So take note that the Amperian loop considers directions or takes note of the directions, and where your thumb points is the direction of the positive current. Here, I1 and I3 are directions of positive current since our thumb points up here when we do the right-handed screw rule, then I2 points downward. Okay? So this is the perspective view of this system or this system of currents. When we look at the top view, okay, where I1 and I3 point out of the page and I2 points into the page, our integration path or our Amperian loop points in the counterclockwise direction. So this is counterclockwise. Okay? In the counterclockwise direction, the currents that point out of the page direct are currents that are positive. So I1 and I3 here are our positive currents. I2 is our negative current. So as seen is this equation here. Okay. Okay. As you see in this slide, in this example, you have a current source that points out of the page. Okay. So at equidistant points at distance r from the current source, you have the magnetic field lines circulating in the counterclockwise direction so that these are the directions of the magnetic fields, so drawn tangent from the field line. When we choose an integration path that is circular but also points counterclockwise, the dot products are always positive. Okay? So the two directions are, or the two loops are parallel, always parallel, so that the line integral here is positive, and this is our right-hand side of the Ampere's law. Compared to the following scenario, where we still have the current source that points out of the page, whereas our DLs are pointed clockwise. Okay, so we still have the same integration loop, a circle that has radius r, but the the path of integration is clockwise. So all the B's and all the DLs are always antiparallel. That's why the right-hand side of Ampere's law is now negative. Okay? So we see here that the direction of the Amperian loop is important, okay, in determining the sign of the right-hand side. Okay? Simply put, we have the following sign conventions for Ampere's law. So you may take a look at them first before we proceed. Consider the following example where you have two current sources, one pointing out the page, this one, and another one that points into the page, this one, and they have the same current magnitude. Okay? Ampere's law states that when we close them using this rectangle right here, so this is a closed path, this is a valid choice of an Amperian loop. Okay? Ampere's law states that the line integral around this rectangle is zero. Okay? But that does not imply that the magnetic field produced by these two current sources is zero. Okay? So the field is nowhere zero around this and this integration path right here. Okay? So as an example, we consider three current sources. Okay? Two current sources point out of the page with magnitude I. Okay? And one current source pointing into the page with magnitude 2i. Okay, so the questions now are the line integrals for path A. So this is path A right here, path B, and path C. Okay, so try this out first before I reveal the solution. The solution now to the problem is as follows. For loop A, you trace a counterclockwise path, okay, so that the out of the page current I is now the direction of the negative current as reflected here, whereas the into the page current 2I is now the direction of the positive current. Okay? What we do is just add these two currents, okay? And we simply get mu naught I for the line integral. Okay? Likewise, for loop B, which is oriented counterclockwise, this enclosed current I here points out of the page and is now the direction of the positive current. So you have this one, mu naught I, and 2I here points into the page. It's now the direction of the negative current. So we have a negative sign here. When we add these two contributions to the line integral, you have the following. Okay? So now finally we have loop C, which now encloses these three current sources, 1, 2, and 3. Okay? So adding them all together, we have the two i's pointed out of the page. So this is negative I, minus I, and 2i here, which now points into the page. Okay, so it has a positive sign. When we take the total line integral, just turns out to be 0. Okay, however, in this example, we know that the field and everywhere is nowhere found to be 0 as sourced by these three currents. Okay, so we now look at this other example here where we have four integration paths, A, B, C, and D. Okay, so now we consider the integration paths all oriented clockwise. Okay, again, Ampere's law does not care about the shape of the integration paths or the Amperian loop. What's important for now is to determine the line integral. So the task here is to basically identify how many currents are enclosed, okay, with considerations in the direction. Okay, so to go about this problem, we now look at the current enclosed by each integration path. Okay, so integration path A encloses no current, so that the line integral there is 0. Okay, so this one. So path B encloses I1, which points into the page, denoted by the symbol. However, if we have a clockwise integration path, into the page is the direction of positive current. So there's mu naught I1 here. Okay. Path C encloses I1 and I2. Okay, so I2 points out of the page, so it now bears a negative sign. Okay. Finally, we have path D, which now encloses I1, I2, and I3. So I2 and I3 here now point out of the page, which is the direction of the negative current when we have a clockwise integration path. So the line integral has this expression right here. Okay? So the start of Ampere's law is basically having an Amperian loop and counting the number of currents enclosed by it, with considerations on which direction is the direction of the positive current, okay, and which currents oppose to that sign convention. Okay, with all of that, we are now ready to calculate magnetic fields from highly symmetric current distributions using Ampere's law. Okay, so the calculations are very similar to Gauss's law calculations for electric fields. We remind ourselves that Ampere's law is given by this equation, where the left-hand side is a closed line integral, which is now proportional to the current enclosed by the integration path. Okay? What we will try to do is to attribute this dl to the length of some Amperian loop. Okay? And what we want is to choose a special Amperian loop such that this line integral here turns into a simple product. Okay? Meaning, the magnetic field lines produced by the magnetic fields are either parallel or antiparallel to our Amperian loop. Okay? So here's how we exploit Ampere's law to calculate magnetic fields of highly symmetric current distribution. First, we identify the symmetry of the system. Okay, so what we do here is to identify whether the current distribution poses some symmetry, okay, or how its magnetic field lines look like. Then choose an appropriate Amperian loop. It should have the same shape as the field line of the system. Okay, so choosing an appropriate Amperian loop turns our line integral into a simple product. And since we have simple products on both left and right hand sides, we can just simply evaluate and isolate the magnetic field. Okay? Then we have an expression for the magnetic field due to these highly symmetric current distributions. Okay? So now we consider the following example where we can carry out Ampere's law very simply. Okay? So we consider a current carrying wire with current pointing to the right. It has a magnitude I here. Okay? With this current source, we know for a fact that the magnetic field lines circle around this current source with the magnetic field at the top pointing out of the page and the magnetic field at the bottom pointing into the page. Okay? So our natural choice of the Amperian loop is a circular one. Okay? So that circular Amperian loop now has length 2 pi r, with r here the location of our field point from the current source. Okay? So with this choice of an Amperian loop, this line integral turns into a simple product of the magnetic field and the length of the Amperian loop given by 2 pi r. Okay? Now that we have the left-hand side, the right-hand side is just now mu naught I. Okay? And eventually, we can arrive at the expression for the magnetic field, which we have derived also using Biot-Savart law. However, we did it in a much simpler way. Okay? We only have three lines here. 1, 2, and 3. Okay. We can now consider a cylindrical conductor where its cross-sectional area is no longer a point, but a circle. Okay? So in this cylindrical conductor, you have current I uniformly distributed over the solid cylinder. Okay? So take note that this current I is contained in the entire cylinder, distributed uniformly. Okay? So at points inside, we may no longer see a current enclosed, which is this entire current I here. Okay? So now we will make use of the definition of the current density, okay, which is now given by the current over the area of the cross section. Okay? So from here, our enclosed current now is given by the current density of the object, okay, which we assume to be uniform in this case, and this area enclosed here. Okay, now this area enclosed is the area bounded by our Amperian loop. Okay, we will see this problem shortly. So we first look at the case where our field point is inside the cylinder of radius big R. Okay, so this is our expression for Ampere's law. Again, we have an integral on the left-hand side and the current enclosed on the right-hand side. Okay, so now we resolve the left-hand side first. Okay, so while this is now a solid object, it still contains the same symmetry as our long long wire. Okay, so that the left-hand side now becomes a simple product, which is now of the form B times 2 pi r. Okay, again we note that the radius here is the radius of the Amperian loop. Okay, now we look at the right hand side, which now contains I enclosed. So again, at r less than big R, this is the form of our right hand side, mu naught I enclosed. However, this I enclosed is no longer the I mentioned in the problem. Okay, since inside the Amperian loop that we considered, we did not cover the entire current I. Okay, now we turn to the current density, okay, which is defined as follows. Okay, so the current density can be expressed in terms of the total current, okay, over the total area of the cross section. Note that this is uniform, so we can make use of the total, so total current over total cross sectional area. Okay, so we now calculate the I enclosed, okay, which is now the current density of the object multiplied by the area enclosed by the Amperian loop. Okay, and the I enclosed is as follows. Okay, this is the total cross-sectional area of our conductor in terms of big R, while the area bounded by the Amperian loop is in terms of small r. Okay, so that the I enclosed is scaled by the following expression: I r squared, small r squared, over big R squared. Okay, now that we have both the left and right hand sides, we can now combine them to solve for the magnetic field. Okay, so again, this is our Ampere's law. We now equate both the left and right hand sides. We now have the line integral, which is now a simple product, and the right hand side, which contains I enclosed. Okay, and finally, we have the following expression for the magnetic field inside this long cylinder. Okay, note that this is linear in R. Okay, so please take time to stare at it properly, okay, and see for yourself, convince yourself. Okay, okay, now at points outside the cylinder, okay, at this region here, R greater than big R, okay, we still have this form of Ampere's law, where we also choose a circular Amperian loop. Okay, the main difference now here is the enclosed current by the Amperian loop is now the total current I. Okay, so now Ampere's law turns into the following form, and now we can simply isolate B and obtain the magnetic field. Okay, so this magnetic field right here is also the magnetic field of a very, very long wire. Okay, so what this says is that a cylindrical conductor behaves just like a long wire at points outside. Okay, so in summary, at points inside the long cylinder, this is our magnetic field, linear in R. At points outside, this is our magnetic field, inverse in R. Okay, inversely proportional to the distance from the center of the cross section. Okay, so we have now covered the magnetic field due to a long wire and a long cylindrical conductor, okay, where we make use of circular Amperian loops. Okay, so this is how your magnetic field due to the long cylindrical conductor behaves. Okay, linear up to big R, then inverse up beyond big R. Okay, now we consider the field of a solenoid. So a solenoid basically is a current carrying wire looped at n number of turns, n here, okay, with some length L. So this is how a solenoid looks like, okay. So now for the following calculations, we will consider the number density, okay, or the number of turns per unit length, okay. So take note of that. Okay, so at some view, you may look at the solenoid as this one, where at the left side of the solenoid, you have currents that point out of the page, and on the right side, you have currents that point into the page. Okay? So for in general, this is how the magnetic field of a solenoid looks like, but we consider the ideal case in this illustration here. So in the ideal case, the solenoid is tightly packed such that the coils are very close to each other. Okay? So on the left side, you have currents out of the page. On the right side, you have currents into the page. In this ideal scenario, you have a uniform magnetic field, okay, that points upward inside the solenoid. At points outside, you have zero magnetic field. No field there. None. Zero, zero. Okay. So in applying Ampere's law, we will consider the ideal solenoid where you have a magnetic field that is uniform inside the solenoid and effectively zero outside. Okay? So how do you apply Ampere's law from this system? So here we describe the ideal solenoid as having n number of turns per unit length and carrying current I. Okay, so now the question is, what is the magnetic field due to this ideal solenoid using a rectangular Amperian loop as shown? Okay, so the labels of each segment comprising the rectangular Amperian loop is important, and we will show it shortly. Okay, so to proceed, we first set a direction for integration. Here we choose a clockwise path. Okay, so here is our Ampere's law statement, where the left-hand side can be decomposed into four integrals, which represents the line integral for each segment. So the line integral at segment 1, segment 2, segment 3, and segment 4. Okay? So we consider b dot dls on each segment. Okay? So we'll see why we have this choice of an Amperian loop, which is a rectangle. Okay? So let's look at each term. So here they are. So for segment 1, this is parallel to the magnetic field that we have in the diagram. Okay? So whatever that magnetic field is, that's B. Okay? It's multiplied by the length of this side, which we now call B. Okay? We identified this side as B. Okay? So on segment 2, which has length W, okay, we have a magnetic field that is perpendicular to this segment. Okay? So that means you have a line integral which is 0. Okay? So on the third segment, we do not have a magnetic field there, so the line integral is 0 as well. And on segment 4, we have the magnetic field perpendicular to that segment there. So the line integral is 0. So we take note of the special fact that there is zero magnetic field outside. That's why the line integral at segment 3 is 0. Okay? We now resolve the right-hand side of Ampere's law, okay, which is this one. So recall that on the left-hand side, we are only left with BD, okay, the contribution due to segment 1, okay. So on the right-hand side, we now determine what I enclosed is. So here, we have a number of currents that point into the page, okay. So note that each current here carries a magnitude of I, okay, and we count the number of turns here as n, okay. So also take note that the right hand side is positive since this n number of currents that point into the page, okay, are all positive due to our choice of the Amperian loop, which is now clockwise, okay. So now that we have resolved the right hand side, okay, we're now ready to express the magnetic field due to this solenoid, which is now this one. Okay, we just isolated B so far. However, the number of turns n that we had counted only valid for this length d. Okay, so this length d here. So to generalize, we now turn to expressing this one as the number of turns per unit length, the small n. Okay. Finally, we have the magnetic field due to a solenoid given as follows: mu naught Ni, or small ni, where n is the number of turns per unit length. Okay? So this expression is very much uniform. I just have mu naught, which is a constant, n, which is a constant, and I, which is also a constant. Okay, so when using Ampere's law, we should see that the magnetic field is indeed uniform inside. And this is what we got here. Okay, so our final example is a toroid. Okay, so in a toroid, basically you have a magnetic material where you can loop your current around, okay, as seen in this figure A. Okay, ideally, this toroid is tightly packed such that at the inner radius, you have you have currents that point in one direction arranged in a circle, such as this one, okay? And on the outer radius of that toroid, you have currents that point in the opposite direction, so out of the page, okay? So basically, this into the page currents are from this inner radius, okay? So pardon my drawing. And the currents out of the page are in this radius here. There you go. Let's see. Alright. There you have it. Okay. So if you think about it, you can basically form a toroidal configuration from the solenoid that we had earlier. Okay. Basically form them into a circle such that we have the following configuration in diagram B. Okay. So to use Ampere's law in finding the magnetic field due to this toroid, we consider three paths. Path 1, so this is inside this toroid. Okay, so path 2, this is within the magnetic material where the wire has been looped. And path 3, which is just outside the toroid. Okay? Okay, so before we proceed, we make the following assumption. So the following assumption is the number of turns on the inner radius is the same number of turns as that in the outer radius. Okay, so on the inner radius, the turns point into the page, while on the outer radius, the turns point out of the page. In this system, we can consider three paths. So the first path is the path where we have zero current enclosed. So this is the location inside the toroid. Since there is no current enclosed, that means there is no magnetic field inside. Okay? On the second path, which is between the windings, okay? So that means we're within the toroid. The enclosed current by this Amperian loop is this bunch of currents which point into the page. Okay? So this one, and this one. Okay? So these currents here. So we count the number of turns as n. So each turn carrying a current I. Okay? And since we chose a circular Amperian loop, okay, it has the following circumference or length. So basically we have the magnetic field due to long wires, okay, with number of turns n. So multiplied by the number of turns n. Okay? So that's for path 2. Then for path 3, which is outside the toroid, we have the same number of turns on the inner and the outer radius. Okay? Therefore, that's just Ni minus Ni. Then the magnetic field is 0. Okay? So the idea is the current is coiled within this toroid to confine the magnetic field inside the toroid, or within the toroid, I mean. Okay? So, so now I implore you to do the following exercise where you have coaxial cables. The inner cable carries a current I pointing to the left, and the hollow cylindrical cable with inner radius B and outer radius C carrying a current to the right. Okay? So the task is to find the magnetic field magnitude at these regions. Okay? So are between A and B, so at this region here, and at this region here. Okay? So the cross-sectional view of this problem given as follows. So the dotted lines trace your Amperian loop. Okay? And this is the preferred view for the current. Okay? So I implore you to try this problem here. Alright? Now we proceed to non-uniform current distribution. Okay? So there are certain systems where you have a non-uniform current distribution. Okay? So the non-uniform current distribution is reflected in the current density as a function of the cylinder radius r. Okay? So Ampere's law takes this following form here. Okay? So where I enclose is now this expression. Okay? So dot product between the current density, which is a vector, and the following dA. Okay? So in non-uniform current distributions, we will consider cylindrically symmetric systems, okay, such that your current density is along the length of the cylinder given by this vector notation here, okay, and the infinitesimal area is the infinitesimal area of the circular cross section 2 pi r prime dr prime, okay. So this infinitesimal area should form the area of this circular cross section, okay, and the normal to that area is along the length of the cylinder. Okay? So with all that, our non-uniform current distributions have this form of the Ampere's law. Okay? Where you only need to worry about this integral here. Okay? So note that I put primes so as not to confuse the r's here with the r on the left hand side, which contains the radius of the Amperian loop. Okay? So I think all of these are better understood with an example. So let's consider one. So let's say we have a current density, okay, which has the following form, linear in R, okay, and C here is an arbitrary constant. So we need to find the magnetic field at regions inside and outside, okay? So to proceed, so the solution is as follows. So we already made the choice of a circular Amperian loop so that the left-hand side is already resolved. So our task now is to solve the right-hand side, or basically the enclosed current, okay? So the enclosed current depends on the limits of integration dictated by the dimensions of our Amperian loop with current, okay? So since we are inside the cylinder, our limits of integration is from 0 to small r, okay? Then substitute j of r to this one, and this is our infinitesimal area, dA, okay? Carrying out the integration into simple steps, we now have this expression for the magnetic field, okay? So in so on the second case, the main difference is the upper limit of integration, as you see here, okay? Note that our current density is only limited to the cylindrical conductor with radius r. So even though the Amperian loop is outside the cylinder, the enclosed current is only limited up to big R here. Okay? So the integrals are the same, so that we can just carry out the integration and arrive at this result. Okay? So usually in non-uniform current distributions, we only consider those that are cylindrically symmetric, so that the integrals that you'll use are very similar. You have j of r and you have dA, which is 2 pi r dr. Okay, so that's it for Ampere's law. If you have questions, you may contact your instructor. So that's all for today. Thank you.